Today we are talking about distance, and you may think we've already talked about distance before. That's something we already know about. So starting out, we're going to look for the distance between 2 points, which is something that we learned about in the first 6 weeks. And to do that, we're going to use the idea of the Pythagorean theorem, which gives us in geometry the distance formula. So if I have a point at -1, -8, we don't have to draw this, I'm just trying to help visualize, and 4, 4, we want to find the shortest distance between those, which would be drawing a straight line between them like that. And to find the distance, we use a triangle, so we find the vertical and horizontal distance. Our vertical distance here, we're going from a -8 up to a +4, so that's 12. And we're going from a -1 to a +4 in x, that's a 5. So then we do Pythagorean theorem and do 5 squared plus 12 squared equals c squared, where c is our distance that we're looking for. So this is a Pythagorean triple, which is a 5, 12, 13. We could also work it out and do 25 plus 144. That gives us 169, which is a perfect square of 13. So we find our distance of 13, and that's the kind of distance we've done so far this year. We're going to be using that and building on top of it with some other concepts about lines that we've been talking about. So hopefully that part seems pretty familiar because we're going to be using it and then developing more things on top of it. So the next warm-up question says, find the distance between y equals 4 and y equals 8. If we were to draw those lines, y equals 4 is a horizontal line at y equals 4, and y equals 8 is another horizontal line up here. So to find the distance between them, since they're parallel, that means the distance is always the same. So it doesn't matter where I go on these lines, we always have the exact same distance between them. And since they are horizontal, I can find that by doing 8 minus 4. So at any given point, the shortest distance straight across to the other side is going to be 4. Similarly, if I have a point and a horizontal or vertical line, it's really easy to find my distance. So I have the line x equals 7, so that's a vertical line out here at x equals 7. And we have a point -4, 13, so that would be somewhere up here. And if I want to find the distance to that line, the shortest way for me to get there is to go directly to the right. So hopefully that's obvious that if we wanted to get to there the fastest, we would go straight from one side across to the other. We're not going to take like a diagonal path, that would be longer. The shortest way to get from a point to a line is to go straight to it, basically making a right angle, meaning that we're going along a perpendicular path. So to get from -4x to 7x, we're not changing y, right? We're going straight across horizontally. This would be a distance of 11. And then the last question here, which I don't expect us to be able to do yet in the warm-up, is to find the distance between these parallel lines, which we know is always going to be the same, but they're not horizontal or vertical, meaning the shortest path between them isn't going to be just x or y. So let's kind of sketch what this one would look like, and then we'll talk about how we could figure it out. So we have y-intercepts of 4 and -4, and both have a slope of 3, which is fairly steep. So we'd have lines something like that, where they're parallel, and the shortest distance between them stays the same everywhere. But to find it, we would have to follow this slope of -1/3 to be perpendicular. So we know the slope of these shortest paths is -1/3, but we don't know how long those paths are. So today we're going to talk about how we can figure out things like this. Alright, so let's look at our notes. First thing we have is the idea of perpendicularity. We've talked about this over the past week and also in algebra. So hopefully perpendicular slope, we can recall, is perpendicular slope is the opposite reciprocal of the original slope. So in that example we just looked at, a slope of 3/1 would become -1/3. So it's going to be flipped upside down and the sign switched from whatever our original slope was. And that's really important because whenever we're finding our shortest path, we're always going to follow a perpendicular line. Next thing was distance formula, so we talked about that in the warm-up as well. The way it's written in geometry is distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And that's really, again, just the Pythagorean theorem expressed with the coordinate points instead of with the distance, the horizontal and vertical distance that the triangle makes up. But this is just a fancy way of saying c equals square root of a squared plus b squared. So you don't have to memorize this formula as long as you can kind of generate it out of the Pythagorean theorem. And then the last thing here is perpendicular bisector theorem. So this is a new theorem that we have, and its converse. So this new theorem says that if we have a line segment or a line, now it has to be a segment because we're talking about a bisector, and we have a point, well, let's first go ahead and make the bisector for the main theorem, and then we'll do the other way around for the converse. So this is my bisector that divides this into two even parts, and it is a perpendicular bisector, meaning it makes a 90-degree angle. So you may recall in the first 6 weeks we talked about constructions and how we could generate this or draw it based on using a compass and making our construction marks out here and finding where they cross and then connecting them. So this perpendicular bisector splits this into two even parts, and what this theorem says, this perpendicular bisector theorem, says if I pick any point on the perpendicular bisector, then the distance to each end point is going to be the same. That was terrible. Let's go from here to here. So it says that this distance and this distance must be the same if my point is anywhere on the perpendicular bisector, no matter how close or far from the segment. So if I make another point here, and I draw these two lines, it says that these two are also equal to each other. So that's the theorem. The opposite way around is, you might guess, going to tell us that a point is on the bisector. So if I have a segment, and I have some point out in space, or on the plane, and I measure and find that the distance is the same to each endpoint of that segment, then I can say that this point lies on the perpendicular bisector. So that's the converse part, is saying that if I know the point has that equidistant relationship, then it is on the bisector. So over here is the converse, and this is the main theorem, which tells us every point on the bisector is equidistant from the endpoints. All right, so the next thing we have is the idea of minimum distance. So we talked about this again a little bit in the warm-up. And the idea here is, think about if you want to cross a street. You're standing over here. That's you. And you want to get across the street as quickly as possible, as far as like the number of steps you take. So you're not going to run this way across the street because you're covering a longer distance than if you ran, say, this way. And then the shortest distance you could make would be to go perpendicular, like straight across the road, perpendicular to the direction the road is running. So this is going to be the shortest, or the minimum distance is always on the perpendicular path. So if we have an angle that's not 90, then we're lengthening the path. And you could even go to an extreme of saying if we had a very small angle, you would basically be running down the road for a long time before you eventually get across it. I didn't even draw the road long enough. So if the road kept going and our line kept going, we could eventually cross the road at this ridiculous angle where this is maybe like 10 degrees instead of 90 degrees, but we're going to be in the road for a really long time. So what we're talking about when we say the distance from a point to a line or between parallel lines is the minimum distance. So the smallest distance that we can cover to get from one to the other. So the way we're looking at this in geometry is we have a point somewhere in space, we know its coordinates, and we have a line somewhere, and we want to find the shortest distance from this point, which is some x and y, to this line, which has some y equals mx plus b equation. So to do that, we kind of need to know where these lines intersect. So if I drew perpendicular here, there would be some point at which they cross. And if you remember from algebra, if we know the equation of, say this is y1, y2, this is m1 and b1, y2 equals m2x plus b2. If we have these two linear equations, we can find their point of intersection using a system of equations. So we're going to talk about how we can find this point of intersection and then calculate the distance between the 2 points. So then we'll have x2, y2 at the intersection, and we can use our 2 points we know about to calculate the distance using the distance formula. The other way we're going to look at distance is between 2 parallel lines, like we saw in the warm-up. So to find the distance between parallel lines, it's basically the same idea as here, just we need a point on this line, and then we need to know where it intersects the other line if we draw a perpendicular path between them. So in this case, we could easily just use the y-intercept of this line as the starting point, and then find the intersection and treat it like this. So basically, you can pick any point along this line, and then turn it into this problem where we're going from that point to the other line. We just know that every point will be that distance from the line because they're parallel. Okay, so let's look at some examples of how to actually do these problems so that we can see the process. So we have this line and this point. There's a graph here, but we don't need the graph. I'll go ahead and draw this one just so we can visualize, but what we're doing here does not require graphing at all. So I'm going to draw the line 5/3 x plus 3. It has a y-intercept here. It has a slope of positive 5/3, 1, 2, 3, 4, 5, 1, 2, 3, and 1, 2, 3, 4, 5. So as usual, this is going to look terrible on this screen because I can't draw straight, but something roughly like that. And then we have the point 2, -5, which is here. So if I want to find my shortest distance, I know that I need to follow a slope perpendicular to that one. So my slope of this intersecting line is going to be -3/5. So let's see if that intersects nice and evenly. 1, 2, 3, 1, 2, 3, 4, 5. It does. That's going to rarely be the case. So a lot of times in these problems, you're going to end up with radicals or fractions or things that don't make nice even numbers like this did. But this one happens to be a nice starter problem, and it intersects right here at -3, -2. So -3, -2 is our point of intersection, and our starting point was 2, -5. Now our last step is just to find the distance between those two. So we're going to take -5 minus -3, so plus -3. So our vertical distance that we traveled was -3, -2. Oh, I did the wrong number. No, minus -2. I need the y value. So we're going 3 vertically, and then horizontally we're going 1, 2, 3, 4, 5, which we get from 2 minus -3 is 5. So using those distances, those x and y distances, we can calculate the square root of 3 squared plus 5 squared. So that's the square root of 9 plus 25, that's 34. Then we need to check if we can simplify. 34 is made up of 2 and 17, which are both prime numbers, so there's no way to simplify this radical. So square root of 34 is going to be our distance from that point to that line. And remember, that's a minimum distance. We could travel further, so we could go just like straight up vertically until we hit this point. But there we would have traveled, what, 11 units, which is much more than square root of 34, because remember, this is a little bit less than 6, so something like maybe 5.9, because square root of 36 would be 6. So we know we're a little bit smaller than that. So traveling like straight up to get to the line would be way, way further. All right, so let's look at another example. I'm just going to make up a line and a point, so this one is pretty much guaranteed not to come out to nice even numbers. So let's start off, and we're not going to graph this. We're going to do it all without graphing. So we're going to start with the line y equals 2/3 x minus 7. 2/3 and 7 should both guarantee that we end up with terrible numbers here. And we need a point. So a point, so 2/3 x minus 7. Let's pick a point in quadrant 1 and just do something simple like 1 comma 4. So that's our starting point, and we want to go to this line. So our process is, step 1 is find our slope. Find m2, and in this case, m2 is going to be -3/2 because it's the reciprocal opposite of that. So we make it negative and flip it. Step 2 is we're going to write the new line equation. Actually, let's write perpendicular line equation. So write perpendicular equation. So to do that, we're going to use our slope and this point and either write a point slope form equation or use substitution to solve for the y-intercept. I'm going to opt for doing substitution this time, and then I'm going to work the problem again and we'll do point slope. So for this one, we're going to use our point and say 4 equals -3/2 times our x value of 1 plus b. So then to get b, we need to add this thing to both sides because it's a -3/2, so we're going to add 3/2. And if you've forgotten how to add fractions, this is a good time to remember that. So to add them, we need them both to be the same denominator. So instead of 4, we're going to think of this 4 as 8/2, and 8/2 plus 3/2 means b equals 11/2, 11/2. So now we're going to write our second equation with this new slope and this new y-intercept. It's y equals -3/2 x plus 11/2. Now, step 3 is we're going to solve our system. Solve system to find intersection. So we now have our original line equation and our new one. We need to solve them as a system of two equations. The nice thing about the way I did it with substitution is we already have both of them solved for y, so I can just set 2/3 x minus 7 equal to -3/2 x plus 11/2, which is, again, not going to be pretty numbers, but no problem, we can still handle it. So this is -3/2 x plus 11/2. Now we can move stuff around and work with fractions, or we can multiply all four terms by a common denominator of 6 to get rid of the denominators. I don't really care which way you do it. I'm going to go ahead and get rid of the fractions and multiply everything by 6. So I'll get 4x minus 42 equals -9x plus 33. So if you've forgotten how to multiply numbers by fractions, when we do 6 and divide by 3, I'm really multiplying 2 times 2, and that's where 4 comes from. Here, when I do 6 times -3/2, I'm doing 6 divided by 2 is 3, times -3 is -9. 6 divided by 2 is 3, times 11 is 33. So if you're not comfortable with multiplying and dealing with fractions, we really need to work on those skills, because you'll need them not only here, but also a lot next year in Algebra 2. So 13x, we bring the 9x over here, bring the 42 over here, equals 75. Oh, I thought for a second that was going to work out nicely. 65 would have worked out well. So we're going to divide by 13. And 13 doesn't go into 75, so x equals 75/13. Terrible number as promised, because I just made up completely random stuff here. So to find y, remember that when we solve a system, we end up finding x or y, and then we plug it back in to find the other one. So I can plug in this x value to either of the two equations. I don't know that either is going to be particularly great here, so I'm just going to go with the original one and do y equals 2/3 times 75/13, plugging in for x, minus 7. So remember multiplying fractions. We just multiply straight across. So this is 150 over 39 minus, and then since we want to combine these, this 7 needs to also be in terms of 39ths. So we're going to do 7 times 39, and that's going to give us a 3 and a 6 and a, like that, 273. And I know I wrote those upside down from how you probably would, it doesn't matter. So minus 273 39ths. And then to subtract fractions, we just go straight across because they're both 39ths. So we get negative 123 39ths. And I can't imagine that that simplifies. Oh, it does actually, because this is divisible by 3 and this is divisible by 3. I know that because if I add up all the numbers here, I get 6, and if I add up the numbers here, I get 12. So that actually means both of these should be divisible by 6, is that right? 39, no, 39 is not divisible by 6, so 3 then. So I'm going to divide the top and bottom by 3 and get negative 41 over 13, and that's going to be my matching y value that goes with that x value. So we now have our point of intersection. Usually it'll be a little easier than that. I won't pick numbers that are quite that difficult, but it is, it's reasonable for you to be able to work with these fractions. Okay, so we found the intersection, and then final step 4 is find the distance. So we're going to use the 2 points, the nice point here and the terrible point here, and we're going to find the distance between them. So first of all, to make that easier, I'm going to rewrite this as 13 13ths, comma, 40 52 13ths. So that way I can easily figure out. So from 13 13ths to 75 13ths, if I subtract that, I go 62 13ths. I need to square that and add. So from negative 41 13ths to 52 13ths would be 93 13ths. I need to square that. Okay, I think that's the point where I'm going to give up on following this through because those numbers are a little too hard to work with. I promise that if I give you fractions to work with in a problem on a quiz or a test, they won't be quite that heinous because I don't want to square 62 and 93 right now in a video. It's going to take way too long. So that's the idea, is we're going to do these 4 steps to find the answer. Actually, I am going to pause the video so you don't have to watch, and I'm going to go through and solve that real quick. Okay, so I've got my 62 squared, my 93 squared, added those together. Divide that by 169, that's all the square root. So I know 169 is just 13 times 13, so I checked if I could divide that number by 13, and I could, and I got 961. And then I had no idea how to factor 961, so I just looked up the factors and found that 961 is actually 31 squared. So somehow, out of all of that, we get a perfect square and get 31 over square root of 13 as our distance. So remember, we're not allowed to leave radicals in the denominator. So we're going to have to bring that up here by rationalizing. To do that, we multiply the top and bottom by square root of 13. We end up then with 31 root 13 over a regular 13. So 31 square root of 13 over regular 13. That is our final answer. And if we wanted to, we could approximate about how much that is. So square root of 13 is between 3 and 4 because it's between 9 and 16. So it's somewhere between 3 and 4. And so we have maybe about 100-ish here, which is about, so I'm guessing this is somewhere around 8 if we actually typed it in a calculator, just doing a rough estimate based on what the square root is, and all that. So there is another way, but we can solve this. So this 4-step process here is how I would go about solving it because it makes sense. It kind of builds on everything we've done in algebra and geometry and is a logical process of working through. So we can find our slope of our new line, write our perpendicular line, find the point of intersection, and find the distance. So the nice thing about that, it's very similar to what we did graphically, right? We drew the graph, then we drew the perpendicular line, we found our intersection point, we calculated the distance. So we're just doing all of those steps, but without a graph. Now, there is a kind of advanced formula that you can just use to solve these as well without doing all these steps. The thing I don't like about it is that it kind of removes you from understanding the process that you're going through. So it's really just feels like plugging into a formula and not understanding what's happening with finding the perpendicular distance. So this is how you would do it step by step. The formula goes, well, first of all, we need this to be different. So we have to have our line in the format ax plus by plus c equals 0. So a lot like standard form, the difference being c is on this side, not on that side. So ax plus by plus c equals 0, and then to find the thing we want, we call this x1, y1. We do a times x1 plus b times y1 plus c. We take the absolute value of that, so we don't actually care if this is positive or negative. We always take this result as a positive, and we divide by the square root of a squared plus b squared. So there's that kind of familiar looking part, but it doesn't really match up, and you can't really see any of what we did in this, at least I don't. So let's see what would happen if we kind of follow this path and if we get to the same result. If not, I messed something up over here. So we're going to rearrange this. We're going to multiply everything by 3 to get rid of our fraction, because we can't have fractions in this standard form. I guess I'll bring everything together first. So we have 2/3 x minus y minus 7 equals 0 once we get everything to the same side. Then we need to multiply every term by 3 and get 2x minus 3y minus 21 equals 0. Then we'll plug stuff in here. So a is 2, b is negative 3, c is negative 21. So we have 2 times the x value that we're trying to get to, which is 1, plus negative 3 times 4, plus negative 21. And of course I could just write those as minus instead of plus a negative, and I'll go ahead and actually correct that and make this minus. So minus that, and we're going to divide by a squared plus b squared square root. So a squared is 4, b squared is 9. Please remember squares are always positive unless we have complex numbers, so negative 3 is still positive 9 when we square it. Hopefully without calculators we don't make that mistake anyways. So we're going to do 2 minus 12 minus 21, that's 2 minus 33 is negative 31. Hey, that's looking good, there's a 31 over there. Remember that this is an absolute value, so I don't care that the 31 is negative. I'm going to go ahead and just say it's 31 and ignore the negative sign, divided by the square root of 13. And before we rationalize, that's exactly what we got from the other process. So we're going to get the exact same result from this formula as we did from the actual process of working through it. And I avoided some of those ugly squares and simplifying and knowing that 31 was a perfect square. So there are certainly nice things about this formula, but it is something you would have to memorize and know how to apply. It won't be, even if you had a star chart, it won't be on there. You have to know how to do this if you want to use this shortcut formula. So you have to remember this kind of standard-ish form where C is over with the A and the B. It has all the same rules as standard form as far as there can't be fractions and that stuff. I'm actually not positive if that would matter. I think it would. Anyways, so if you want to memorize this, you are more than welcome to use it to find the distance between a point and a line. And remember that if you're doing between parallel lines, you just pick any point on one of the lines, that becomes your starting point, and then you follow this exact process to find the distance. All right, so that is notes for today. There's practice problems to do on Canvas or handed out in class, so make sure you work through those.